Okay, we should probably get started. If you are, this is your first time at Yocto Project Summit, and you have already been through the beginner class, and certainly the slides that we're going to be going through today in this room, I would suggest heading over to Mickeldor. The beginner class is intended to be for people who haven't done Yocto Project before, or perhaps have never been to formal training for Yocto Project before. If you've been using Yocto Project at all, you will probably find that that many of the things we're going to be talking about today are probably things that you already know. And so you're best be served by going over to Mickeldor. It's the other Zoom room. Indeed, there were 2 links sent in the emails to us all yesterday, and you'll find that the hands-on coding sessions and other sessions happening in Mickeldor will be probably more relevant for your further learning in this area. For everybody else, if you have not used Yocto Project before, or indeed are trying to get started with Yocto Project, it's a bit of a steep initial learning curve. This is the room for you, and indeed we will be going through all of the sort of beginning steps, the introduction to how all the stuff fits together, how it all works, and so on. The idea of this and the next presentation that will be in this room is to get you from 0 to 15. Okay, so this isn't all the way up to being fully versed in all things Yocto Project. There's an awful lot of things beyond what we'll be talking about today, but hopefully at this point, at least you'll be at a point where you can then function at least within Yocto Project to the point of understanding how recipes work, how to build images, and that sort of thing. The talks the rest of this week will minimally make more sense, and hopefully you have a starting point to get further down the path in using both learning and using Yocto Project and its the technologies that make it up. All right, so this is actually a series of 2 talks all in one slide deck. This isn't Google Slides. We like to use Google Slides for this class because we tend to update them for each talk. Again, if you have been through this class before at a previous Yocto Project Summit, you will find that there is very little new with this. This is the same talk we give each time, precisely because people that are new to the project, of course, are new to the project and therefore haven't seen this slide deck before. Again, if you have seen this slide deck, it's worth going to the other room. You will be better served by the content that is there. But otherwise, today we're going to be talking about creating a custom embedded Linux distribution for any embedded device using Yocto Project. It's a bit of a grandiose title, but what we're trying to get across here is that Yocto Project isn't tied to a particular way of doing things necessarily, or sorry, a particular project or a device that you're building it for. You can basically make it do whatever you need to do for whatever you're trying to build. Now, starting from a reference design that's already supported, of course, will be that much faster. But to a large degree, you can basically do whatever you want to with it if you know, if you can get the code to work for it. The building of the image to go onto the device, Yocto Project can handle for you. Today, the 2 presenters will be myself, Behan Webster, and Tom King, who will be doing the second session, talking about images and that sort of thing after the midday break. Depending which time zone you're in, of course, that will be roughly in 3 hours, but it'll be lunch for some of you, dinner for others. It'll be breakfast for me. So there you go. And these slides are under the CC by SA 4.0 license. You will find that there's a bit.ly link in the bottom right-hand corner of the page here. If you want to follow along, that is the link. That bit.ly link will take you to this set of slides. In fact, if I could get somebody, please, to try and I also put the link in the chat. a little bit earlier, I think, what, 10 minutes ago. If somebody could click on that and just verify, please, in the Zoom chat, whether or not you're able to load those slides. Just before we go on, I want to make sure everyone can get. Yep, thank you very much. Sometimes there's some permission problems. Just want to make sure that it works. Thank you. That's great. All right, so let's go through all this, how this fits together. What is the Yocto project? So the big thing about this is understanding what it is. A lot of people will confuse what Yocto project is with other things. The thing to understand is that the Yocto project is it's an umbrella project that has a bunch of other things under it. It's made up of a lot of other things. Now, a lot of work, of course, is done as far as the Yocto project is concerned, but to a large degree, it's a number of tools and best practices and support for various things all in one place that's been tested and put together. So it allows for things like rapid evaluation of embedded Linux on many off-the-shelf boards, both ones that are officially supported by Yocto project and others that have support for, or at least BSPs that are available on the Open Embedded website. It officially supports 4 architectures with a 5th hopefully coming soon, and that's 32 and 64-bit versions of x86, ARM, MIPS Power, so PowerPC basically, and RISC-V. That is the one that's still a work in progress. Open Embedded supports it. Yocto project has support for it. It is not, last I checked at least, it is not officially supported yet, but that the idea is to have that officially supported hopefully in the near future. The support of a particular architecture is based on the members of the Yocto project, and certainly RISC-V requires one of the members of the project essentially to sponsor it, is my understanding. The next thing is that the actual Yocto project core part of the code comes from the Open Embedded project. One of probably the biggest confusions that people have with Yocto project is it feels and looks a lot like the Open Embedded project, and the Open Embedded project looks an awful lot like Yocto project, and that's because there's a tremendous amount of overlap. In fact, the core parts we're going to talk about a bit later are developed together. Okay, and many Yocto project members are in fact also Open Embedded contributors, and vice versa. So the confusion is purely because people work with basically both sides of that fence. Open Embedded is only a tiny bit different than Yocto project in some ways, in various technical ways, but to a large degree the outcomes are the same. And indeed, a lot of the code that goes into Yocto project, indeed almost all of it, is first added to Open Embedded and then pulled into the Yocto project side of things. You can almost think of Open Embedded and Yocto project as kind of like Open Embedded is kind of like Debian. Yocto project is more like Ubuntu, and some people will take offense to that. What I mean by that is a lot of the base technologies go into one. They are pulled in, stabilized, and fully tested and made easier for everybody to use in a standard release format as a part of Yocto project. Although Debian has its own release cycle now, originally it was a bit more like Arch in the sense that it was at the very beginning it was a rolling release, which is one of the reasons why Ubuntu came along. The other thing that's nice about the Yocto project Open Embedded part of it is that when Yocto project came along, the idea of basing something on top of Open Embedded was made possible by the addition of layers. And layers, of course, are something we take for granted these days, but they're really the killer design that actually allowed for this to happen. What it means essentially is you've got your core code. It's called Meta or OE core. That is the base for everything else. This is a shared layer or shared code between the two projects. And indeed is the core code of both projects and how they fit together, co-owned, co-developed by both projects. Other layers put on top of it, in fact, can make it into other things. We'll talk about exactly what those layers do in upcoming slides, but things like Meta Pocky, Meta Yocto BSP, and then other layers on top of that will allow you to customize exactly what it is you want to do without actually having to change the code directly, like you would certainly in the past, or indeed with other options to Yocto Project that do similar things. So again, the Yocto Project specifically is an umbrella organization. It is a part of the Linux Foundation. Fun fact: the Linux Foundation is, of course, an organization that hosts other open source projects, amongst other things, on behalf of member companies. It is an organization that fosters open source between different companies, collaborating on the what I call the boring parts of software, the part that everybody does and therefore is boring. It's not the interesting part that ultimately you know that you buy from a particular vendor. It's the part that everybody uses. The Linux kernel was the first collaborative project at the Linux Foundation. We didn't call it we didn't call it that back then, and indeed it's kind of a special project at the Linux Foundation. The first actual thing that we called a collaborative project, the first project at Linux kernel at the Linux Foundation, in fact, was Yocto Project. So these days, Linux Foundation has a ton of collaborative projects doing all sorts of things in lots of different industries. Yocto Project was literally the very first thing after the Linux kernel, and indeed the blueprint from which the whole collaborative project model was put together, and indeed what led to what we now have with the Linux Foundation's many different collaborative projects. The Yocto Project is an organization and a group of people that is backed by multiple companies, all interested in one thing, and that is, in this case, making embedded Linux better, more manageable, and easier to build things. And indeed, Yocto Project, to a large degree, has become pretty much the de facto standard for building certainly complex things with embedded Linux. And certainly in industries where you're building multiple versions of the same thing, or indeed multiple products in the same product line and that sort of thing. There are a lot of very large companies that use Yocto Project in order to make the various lines of products that we use every day. In many cases, products that we're not even aware that use Yocto Projects. It's actually quite fascinating that at this summit, we've actually found all sorts of companies that we didn't actually realize were using Yocto Project to make things happen. And basically, if later on you're in the social part of the conference and you're using Yocto Project at your company, please let everybody know the number of people that use Yocto Project and then don't actually let Yocto Project members know that they're using it is significant, and it's always nice to hear what people are using it for. Yocto Project, as I said, also co-maintains the open embedded core and other tools like O-Package and that sort of thing. Again, all the core software is managed essentially by both projects. To a large degree, the way that works is that the contributors essentially work with both projects at the same time, and therefore both projects are responsible for making things happen. The really big architectural changes tend to happen within the open embedded side of how the projects fit together and then are pulled back into Yocto Project. Again, a lot of the stabilization and long-term support and other kinds of things, those are done more on the Yocto Project side. So whereas one is more of a rolling release, in that way, more like an Arch or a Gen 2 style thing, on the Yocto Project side, it's much more something where there's a much longer term support for it. So say Ubuntu or Red Hat style of making sure it works and then updates thereafter to make sure it stays around. And of course, there are long-term support versions of releases rather that come out every 2 years. As far as the project governance is concerned, it is organized under the Linux Foundation. It is a split governance model in the sense that there are two groups of people that guide what is done in the project. There's what's called the technical leadership team and the advisory board, made up of participating organization. Essentially, what you have is member organizations that essentially can come together and talk about the kinds of things that they'd like to see as a part of a project and have some kind of say because of the money that they pay into the project. The actual technical decisions, however, are made with the technical leadership team, however. And the idea essentially is that the decisions that need to have technical, technical knowledge and have far-reaching effects are made by the right people. And so there are sort of broad strokes that are made by one group of people. There are very specific technical decisions that are made by the other. Now, the Yocto Project member organizations change on a regular basis. This may not be an entirely up-to-date list of member organizations, but indeed, there are 3 levels of membership, and indeed the level basically is indicated by the amount of engagement they have with the project, generally money and engineers that work on the various parts of the code and that sort of thing. You'll find that there's quite a lot of value by having all these very large companies working together to try and make something that works across the entire industry. And indeed, it's because of these very organizations that are putting effort and money into Yocto Project that we have what we have today with the code base, and indeed why so many vendors now ship with at least minimal Yocto Project support with their parts or assemblies or single board computers or whatnot. It's become the de facto standard for basically the entire industry in a lot of situations. Oops, wrong way there. Yeah, now Yocto Project is designed around the idea of building packages. And then from packages, we build bootable images. Now, this is a little bit different than a lot of other build systems. A lot of other build systems go essentially use something like make. They build the binaries, the various files that are built, and then you install them into the place that you want them placed, and copy that the directory that you make from the install onto your embedded target, and away you go. Yocto Project, we have an extra step, and we go through a build, install, package step, and then from the package step, images are then built. Now, this sounds like an extra step that isn't strictly necessary, and one could argue that it isn't. But the reason why this is really important is because by packaging things, the authors of the recipes that make up each one of the packages are deciding the classification of the different files that go into the different packages. What that means is that we can distinguish between what makes the binary, what makes the development files, the man pages, and so on. And so the nice thing is on the embedded target, we can actually say what of that we want installed, instead of installing everything on the target, or some other build systems will install everything and then delete things that aren't needed and that sort of thing. Instead, with Yocto Project, and Open Embedded for that matter, things are built, made into packages first, and then only the packages that we need are then used to build the image that eventually goes onto the embedded target. It gives you a tremendous amount of control as to exactly what it is that's going to go where in your system. The package format itself, I would argue, doesn't actually strictly matter. The options are RPM, Deb, and iPackage. The pedantic side of me, being a long-time Debian developer, is that one of these is a better packaging format than the other. However, to a large degree, the way we use packages within Yocto Project, they're effectively smart tarballs, and so the actual format itself probably doesn't matter to a large degree, unless you're planning to use the packaging system on your eventual target in order to do the equivalent of an apt update or or upgrade rather, or a DNF upgrade or whatever. The actual packaging format is just a way of putting things together so that you can then eventually get them into the image format, and that's the bulk of the value of the packages here. The packages themselves don't even necessarily follow the upstream the Debian or RPM standards for exactly how the package is put together. Again, they are used in a way to house files that will eventually go onto the image. The packages built by this build system are not up to the same degree of value that you'll find from the individual projects from which these packages come from, and because that's not the point. The way packages are normally built essentially is from within the packaging system. In this case, packages are the output of the packaging system. It's a strange distinction. Just understand that packages are essentially a tool as a part of the build system, as opposed to a necessary output, which is what is used for actual Debian distributions that you would use on your desktop or server or whatever. They're a step in the process to get to an image. The next thing is Yocto Project does have a 6-month cadence. There is a release in April and then in October. And the nice thing about having the 6-month cadence, like a lot of other open source projects have, is of course that you always end up having another version coming out twice a year. April and October have become a really good time to do that, being 6 months apart, but also being a time when everybody else releases their software at the same time. It's also not, at the very beginning of the year, the middle of the summer or winter, depending where you are on the globe, or for that matter, it's not right before Christmas either. A lot of projects in the past have had releases at the end of the year, and that always conflicts with holidays for many people and other things like that. Again, depending where you are in the world, but by doing October and April, things become a lot more straightforward. The other thing that's nice about having the 6-month cadence, of course, is you have quite often near the latest versions of things like the stable kernel, different tool chains, packages, documentation, other utilities, anything new that's come along. One of the great things about this particular conference is that, of course, we get to hear about what's happened along that at the same time. We try to run these conferences just after each release. So we tend to run them in sort of May and then November after the release, in part because a lot of the people that put on these conferences, of course, are working on the release, but also in many cases that we can talk about what just happened to a large degree. Oh, and it is worth mentioning, thanks, Dennis, that there are in fact binary OE distributions and packages that are also available. Indeed, there are things that are built with the technology that's behind Yocto Project, which is open embedded, that can in fact provide binary packages. It is true. It is true. In that case, the binary package format matters more. That is a valid point. But when it comes to actually building something like an image, normally to a large degree, the decision is less important, is I guess all I'm trying to say. The Yocto Project, again, along with the Open Embedded Project, also supplies things like the ESDK, which is the Extensible Software Development Kit, a tool called DevTool, which is increasingly becoming a very important utility to allow you to do development with Yocto Project. Yocto Project is in fact an image builder. It's a mechanism for building something that goes onto your target. DevTool essentially, along with the ESDK, allows you to take what is built with Yocto Project and then develop code along that will then work with that image. And then Toaster is in fact a web interface to the build environment. And indeed, we'll be looking at some of these a little bit later, so we can see how they work to a certain extent. Yocto Project itself has a number of different release versions that have come out over the years, and the most recent ones, of course, are the ones on the lower right-hand corner there. But you'll see that the LTS versions, in this case, are Dunfell from 2020, April 2020, and Kirkston from this year, April 2022. You'll find that, again, to a large degree, like other projects, every 2 years in April will be when the LTS is, and the ones in between, of course, are development versions that come along. If you're going to be building something for a long time, it's best to use one of the LTSs to move on from there. There was a and of course, Mickledore and Langdale, of course, the names were two rooms. We've recently adopted the idea of naming our rooms after the current and next release of Yocto Project. So again, as I've said a number of times, Yocto Project is based on the open embedded core or OE core layer. It is the base layer of how everything gets fit together. You'll find that the metadata files that make up the open embedded core layer, in fact, there's over 800 recipes that make up the ability to build specific boot images. This support includes things for things like QEMU, hardware, quote unquote, hardware target, graphics, networking, kernel recipes, communication recipes, multimedia, which basically means audio, and so on and so forth. So basically, you'll find that the core functionality that makes up open embedded in the Yocto projects tends to be in this layer. Anything that's common across all other things tends to be pulled down through the different layers until it makes it into open embedded core. And so OE core essentially has grown over the years for a number of reasons, but the biggest reason is that if something is used enough, essentially it becomes a core recipe so that it can be used by everybody. And so you'll find that certainly in Yocto project, although there are many different layers that go on top of it that ship with Yocto project, in fact, the number of recipes within those layers, in fact, has dropped over the years, or at least have moved between those layers in order to make things more useful for others to use. The entire point of layers is reuse. And so by putting things into OE core, essentially, recipes can be used as widely and in as shared a fashion as possible. And again, the open embedded project is the core code, represents the core code in the Yocto project system. Indeed, the major parts that make that up are Bitbake, which is the build tool, and indeed the core interface you use when you're building images and recipes and so on, but also all of the metadata and configuration files and base technologies that make up what ends up going into a Yocto project release. And again, Open Embedded is continually working on this code. It is a rolling release system, whereas Yocto project will take a specific version of Open Embedded, or snapshot of Open Embedded rather, and then stabilize and test it and make a release from it. And then finally, we have, there's also a central, Open Embedded also provides a central point for different layers that people make available, some officially, some unofficially, but ultimately they all go into what's called the OE layer index. This is a website that allows you to see which recipes are available as a part of different Git repositories. We'll show you this later as well. It basically provides metadata, names, URLs, support, and a way of searching for recipes that do specific things. So one of the questions just came up is, where do you get the inspiration for your release names? The release names, some of them perhaps have obvious, retrospectively have obvious places they come from, or at least perhaps you can figure it out. But to a large degree, the names come from Richard Purdy, who is the Yocto Project architect. He basically reserves the right to not tell anyone where they come from. So you can perhaps guess what they are, and I gather that some people have come close to guessing exactly where they come from. I certainly have my my suspicions and theories, but Richard has told me several times that the point of naming things in an obscure way is some of the fun that he has, and indeed one of the criteria is that there is always a naming scheme. And the scheme is not trivially Googleable, and basically it's he tries to make them somewhat obscure. So one of the fun things about Yocto Project, of course, is guessing where the names come from. And because we're live streaming here, I'm not going to spoil anything by providing my particular providing my particular theories on what those are, because if I'm at all right, that might spoil things. Yep. See, and that's the thing is, yeah, indeed, I believe that the name ones are indeed those are indeed the case. The ones that are in the chat there. As far as I know, that is true. So what is Bitbake? Bitbake is, of course, the main thing that comes along with Open Embedded and is used for Yocto Project. You will find that there is to a large degree a food related theme throughout Open Embedded and the Yocto Project. We talk about recipes, we talk about baking. You'll find that the core of Bitbake is called Cooker. Of course, we've got Toaster. There used to be an older tool called Hob. Basically, these are all ideas surrounding the idea of taking constituent components and putting them together in a particular way such that you then get an output, much like baking or cooking. Bitbake, of course, refers to that. And so the whole idea behind Bitbake is that it is in fact a DSL or a domain-specific language. It is built on Python, originally Python 2, now Python 3, and provides a very flexible mechanism for defining how to take, again, your constituent inputs, which are your metadata, and then, of course, take you through a series of tasks that will then allow you to build an eventual binary output that will then go into the eventual image. And so it's essentially a way of taking ingredients and baking those into whatever, baked goods that come out the other end, essentially. It does provide a tremendous amount of tooling and conventional ways of putting things together, making things work. It will, of course, point out errors in what you've done, and tries its best, essentially, to do what I call melt your CPU. Bitbake tries extremely hard to make your build as fast as it can, because there are so many steps involved in making things reliable.
It's better.
There are so many things that are used to put things together with Bitbake. Of course, it tries its best to put things as parallel as it possibly can. The idea with Bitbake, of course, is that because it is trying to parallelize things as much as possible, of course, it means that your CPUs are essentially up to 100% as much as they possibly can be. And so you'll find that certainly if your machine does not have adequate cooling, it will eventually downclock to try and protect itself. It basically will try to overheat your computer to a large degree by building as fast as it possibly can. Tom King, who is the presenter of the next half of this particular presentation after the midday break, if you ask him about it, he will tell you a story about teaching Yocto Project at one point, where somebody tried to build an image on their Microsoft Surface laptop, which of course is more or less a tablet with a keyboard, and it literally stopped working with a big black spot on the back of it where the CPU was. It literally melted the CPU. So I always had that as a bit of a joke. He said, no, that's actually a thing. That actually happened to him. And the best part of that is they had to go out to buy something quickly, bought a Chromebook, and ended up SSHing over to a colleague's Xeon laptop and did the rest of the course that way, which always made me laugh. But anyway, there you go. That's Bitbake. It melts CPUs. It does its best to basically build things as much as it can in parallel to try and make your build go as quickly as possible. Again, the more cooling you can throw at machines you're using Bitbake on, the better. Has been my experience. The metadata, of course, is the input to Bitbake, and there's a lot of it, and we'll talk about all the different ones that are there. But the big thing to understand is that metadata is made up of a series of recipes, each recipe themselves being metadata, which of course is organized into a series of layers, which allows you to reuse code between different things. You'll find that to a large degree, metadata is something that you are spending most of your time managing when you're building things with Yocto Project. The important part of metadata is designing it in such a way or maintaining it in such a way that you are doing the minimum amount of maintenance you possibly can. For people who work on projects, and certainly that work on the core technologies of Yocto Project, you're always messing around with metadata to try and make it as flexible and as useful as possible. The big problem with metadata, of course, is the easiest way of updating it, of course, is the whole clone and own way of doing things. Of course, long term, from a maintenance perspective, that's a very bad idea. It's always best to put things together in a what's sometimes called a dry mechanism, a don't repeat yourself style of development. And you'll find a lot of the things that come along with Bitbake and Yocto Project essentially allow you to try and make things as simple as possible. Yeah, and if I could just ask everybody to please keep themselves muted while we're having the conversation. Please ask questions in chat if you can at all help it. All right, so what's next? So next thing we have is Pocky. Now, there are a few people on in the room today that of course have been around from a very long time in the open embedded and Yocto Project mechanisms, and you'll find that amongst all the project members, you will find that this word is pronounced differently by various people. Some people say Pocky, some say Pokey. The official way of pronouncing this, if you talk to Richard Purdy, is Pocky. Pocky was named after the chocolate-covered pretzel that's quite popular in Asia. It is you'll find it at actually most convenience stores, certainly around North America and Europe that I've looked. Pocky comes in lots of different flavors and so on. It's spelled with a C, however, P-O-C-K-Y. Pocky, of course, is the reference distribution of Yocto Project. It's basically the starting point for whatever it is you ultimately want to build with Yocto Project. Because Yocto Project is a way of putting together your own Linux distribution, there needs to be an example starting point showing you what is possible. Pocky is that example starting point to give people a way of building what you actually want to build. This is why when you get when you clone the Yocto Project, what you're actually cloning is Pocky. It's not that the Yocto Project is Pocky. It's not that Pocky is Yocto Project. Pocky essentially is an imagined starting point, giving you an example of how to put things together. You could put things together differently if you wanted to. That's fine. Pocky is essentially the name of the repository that we download with Git, but it technically is in fact a layer, meta Pocky being the layer that actually makes up the distribution. namespace collision, but anyway, there you go. But as I said, it's not a requirement, it's merely a starting point. We'll talk more about distributions later, but you do not need to use Pocky. You can build your own distribution instead to replace it. Again, Pocky just being a starting point for that. But you'll see, of course, that in the layer model, we have Meta OE at the bottom there, or sorry, Meta, pardon me, or OE core, pardon me. Meta OE is something else. On top of that, the first layer above that is typically what's called the distribution layer. This is Meta Pocky in the case of the reference distribution. And this, of course, provides you the idea of how things should be done as a part of your build. So it provides things like branding and the what I like to call the horizontal decisions across all of your recipes. So you'll find that there's a number of global decisions that are made here in order to design how things go across all of your recipes. This is the flavor of how things are going to be put together for the rest of your system. Above that, you start to get into things like the BSP, the UI layers, and then ultimately up into the product and other kinds of layers that come above it. You'll find that in a lot of presentations surrounding the Yocto project and Open Embedded, it kind of looks like there's a fixed number of layers. There are not. There's as many layers or as few as you want. The more you stratify the decisions and metadata that you use, the more you can reuse them to a large degree. The tendency, of course, is to start adding code at a layer near the top of the stack. And then the more generic, the more useful that metadata becomes the further down in that stack. Basically, recipes tend to get moved from layer to layer, tending towards the very bottom layer that it can move down to, which of course for many things is OE core. If recipes are used within your company, of course they may end in whatever recipe layer you maintain as a part of your particular build that you're making at your company, which would be a little bit further up. But again, Pocky is an imagined starting point. You do not need to use it. I've seen lots of people come up with their own distributions, Pocky something. You don't need to call it that. You can call it whatever you want. Again, Pocky is just an imagined starting point. So, you know, what do you get with Pocky? And again, what Pocky ultimately gives you is that starting point. It's actually a number of checkouts or clones of a number of other Git repositories that have been stabilized together. The major or the first thing that comes with Pocky is, of course, Bitbake itself. Now, the version of Bitbake that you use and the metadata that comes with the rest of the system, these need to be matched. You will find that the changes in OE core and Bitbake change in lockstep.
Yeah, it depends the changes between the two PAR files, but yeah. If you add, for example, this 61850 server instance, it should restart.
Okay, so
yeah.
All right, 1 second here. Yeah, I'm not sure how that works, what's going on exactly, but I think somebody keeps on unmuting. Yeah, I just muted him. But yeah, I'm not really sure that's the third time that's happened. Sorry about that. In any case, Bitbake ultimately is that starting point. Again, it changes in lockstep with OE core. As changes are made to OE core that require Bitbake changes, of course, those happen as Bitbake changes. The changes are made in OE core, and so you need to make sure that Bitbake matches essentially the version of OE core you're using. Pocky is great for that, of course, because they come together. Whereas things like Make and Bison and GCC and whatnot, you may install those on your distribution, your Linux distribution, from your upstream package manager for your Linux from your Linux distribution provider. Bitbake is not one of the things you would you would apt install or DNF install and so on. The reason why is because Bitbake it is very much tied to the metadata you're using. So when you get a specific version of Open Embedded, Yocto Project, whatever, there is a matched version of Bitbake that comes with that at that same time. Using a newer version of Bitbake with an older version of metadata doesn't necessarily work, and vice versa. The reason why, of course, is because metadata, the names of the variables and so on, these are changed at the same time in those two places. So that's the first part is Bitbake itself. The next thing are various build scripts. You'll find there's a number of infrastructure scripts that come along with Bitbake. These are other utilities that are used in concert with Bitbake, things like DevTool, things like Wick, and other things like that. There's a number of different scripts and utilities that build upon or work alongside Bitbake to make all these things happen appropriately. Many different tools. They end up in the scripts directory. We also have OE core, which we keep talking about. It's where the bulk of the code that makes up the build system, along with Bitbake, that we use. Again, it's that base layer that we build things on top of. What makes Pocky, of course, is the layer that actually makes it into distribution, and that's of course Meta Pocky. That's the distribution layer. And then there's a number of reference BSPs, and these are essentially added so that there is both a starting point for you building your own BSPs, for instance, but also it provides a test bench to make sure that Yocto Project itself works minimally with certain single board computers. You'll find that for each architecture that's supported by Yocto Project, there's at least one single board computer that represents that architecture that is tested on a regular basis in the automated build system to make sure that it'll in fact still work. So as things are changed and pushed to Git, essentially there is a automatic continuous integration that then also tests minimally in QEMU, but ultimately also on target boards to make sure that it in fact works minimally on real hardware to make it all fit together. And these are provided as part of the reference BSPs. For each release, they minimally follow the best practices for that particular release. And then there's the crowning part, in my opinion, of Yocto
no,
Project,
it's only on
and
the IO.
that is the Yocto Project documentation. And the Yocto Project documentation is ultimately was started originally by someone who sadly is no longer with us, but who did a really great job of starting off the documentation part of the project. The best part about this is that you'll find that almost everything in Yocto Project is not just adequately documented, but it is actually very well documented in a lot of cases. That the biggest problem with the documentation, probably in Yocto Project, is there's objectively a lot of it. And so sometimes people will say it's difficult to find things. There is, in the new version of the documentation that we now have, which was put together by Nico when things changed hands, is of course it's now done in such a way that there's a very excellent search engine to find things. And so the documentation in this project is, in my opinion, bar none, the best. Certainly in open source when it comes to describing how everything gets put together. Indeed, if you need to know the details as to how something gets fit together, if it's written down somewhere, it's probably in the documentation. Does that mean everything is documented? Perhaps not. I guess actually technically Michael Upton now actually maintains those documentations. Thank you very much, Michael. But indeed, those are available in Git and are kept up to date quite wonderfully. Yeah, not everything is documented. I realize, but like I said, by far some of the best documentation that we have in open source. and somebody has to keep it all together. And Michael is doing a fabulous job. Indeed, he more than happy for other people to contribute documentation as well. So let's put it all together. Yocto Project, big collaboration project, lots of people coming together to try and solve big problems, to try and make embedded Linux easier for everybody else. The core of the build system and everything, of course, is open embedded, and that project provides most of the metadata, most of the core recipes. Indeed, even the recipes that come from the Yocto project are first typically added to Open Embedded and then pulled back into a Yocto project release. Bitbake, of course, the core build tool, and indeed the major interface that most people see. This is of course what all the different metadata is based upon, is the tool itself. Pocky, which of course is the Yocto project reference distribution, and indeed the starting point for actually building something with all of these tools in order to build an image for a particular thing that you're trying to put together. And this, of course, is the classic drawing that you will actually see both in documentation and certainly in other presentations. It gives you an idea of the flow of information through the various tasks, where the metadata comes from and that sort of thing. I'll just point you to the top of the screen here. And this is these orange areas at the top here. These are your inputs, your code inputs and so on. This is where all your upstream code comes from, perhaps local code or anything that's in a source code management system of some sort. And this is where we ultimately get all our code from. This is typically external to the project that you're building. So you're pulling things in from public or private sources. But the rest of the system essentially is pulling specific versions of that software using build sequences that are part of the metadata in order to build the eventual image. And so we now need the mechanisms to pull in those specific versions to make that work. Just skipping over source mirrors for a second, we'll go down to the left-hand side here, these red things, and you'll see that we have a number of different things that make up our metadata. The first one is user configuration. This is your local.conf file. This is how you describe what metadata will be used in order to build whatever it is you're trying to build. And so this is your local, I would argue, global configuration for the project that you're dealing with. We then have the various metadata files. These are your recipes, typically the BB files, the patches and other things that make up the individual recipes for the things you're using. Also, some of those recipes, of course, will reference other recipes through dependencies and whatnot. Certainly things like image recipes or package groups and others will essentially pull in other recipes through dependencies, both runtime and build dependencies. We also have machine BSP configurations. This, of course, comes from your BSP layers, and again, pulls in metadata for different hardware, kernels, bootloaders, things that touch hardware more than not, and describe exactly how to build something for a specific target, as opposed to just generally across all targets. And then finally, we have what's called the policy configuration. This is your distribution. This is your distribution layer stuff. And again, these are the horizontal decisions that are made across all of your recipes that come from the distribution layer. And again, the idea here essentially is this is metadata that isn't specific to a particular recipe. It's not specific to a particular piece of hardware. It's all the other things that make your distribution. And those four things then make up the inputs for where to get the source code, how to build it, and how to ultimately put it together in such a way that it'll work on your target. Now, the major thing that you get from your metadata, of course, is where to find the source code for each one of those recipes. Those, of course, come from the orange upstream project sources up at the top there. The problem is that these are not always available. And so for various reasons, servers can go down. For whatever reason, maybe networks fail or whatnot. And so sometimes those things are not available upstream. And to that end, there are what are called source mirrors. Those live between those ups, or rather they don't live between so much as they live as alternate sources of that same source code, just in case the primary mechanism goes down. Now, there's technically something called a pre-mirror we're going to talk about later as well, but for the moment, we're just going to look at upstream sources. If those fail, there is a source mirror. The way this works, certainly for the Yocto project, is that there is a builder that runs on a regular basis, and a part of doing test builds, of course, is downloading the source code. In order to do so, these are then put onto the source mirror in such a way that if the primary upstream source code repositories fail, Yocto project will automatically fail back to its the source mirror that's provided by the project. Indeed, internally, you can set up your own source mirrors in a similar fashion if you so wish. The mirror that you use can be set through, of course, the metadata on the left, typically your user configuration, although technically you can set it in one of the other layers as well, like your policy configuration as well. So these are all of your inputs. Everything from now on, you'll notice is largely in that big blue area in the middle. This is the actual build system itself. Arguably, this is what Bitbake does. Okay, so the things in red largely come from a weak core, or indeed the other layers that you provide. Bitbake, of course, pulls all these things together and ultimately gives you three outputs: your package feeds, images, and ultimately your SDK or development environment. So we'll find in a second that everything's broken down into a series of tasks, and Bitbake runs those various tasks sequentially for a particular recipe, but in parallel across many recipes, just to overly simplify that process. A bit more complicated than that, but just for the moment. The first part is called the fetcher, and what the fetcher does, of course, is based on the metadata. It then knows where to get the source code from. It will then download it or copy it appropriately, depending on what source URI you provide. You provide a URI that indicates whether to get the source code from Git or Subversion or from a tarball, maybe a local directory, whatever it is. There's probably a fetcher that supports it that will download the or get the source code from the appropriate location. There is a second task after that, depending on what kind of fetcher you use, called that's the unpack step. In the case of a tarball, of course, we have to unpack it. That's not shown in the drawing here. Indeed, depending on your fetcher, you may or may not need the unpack step at all. In the case of a Git repository, for instance, it will clone it to a directory. There is no unpack step or other task. After that, there is an optional patch step or task. And what that will do is it will then give you the ability to add patches on top of whatever source code has been downloaded from the upstream locations. The reason for that is simple. So in some cases, there are patches that have not made it upstream yet that you need for whatever reason. In some cases, there are policy changes to the code that you need to have. You'll find that most Linux distributions maintain their own patches on top of source code for similar reasons. Maybe a file needs to move due to policy. Maybe there's a compile bug against a particular version of compiler that you're using. For whatever reason, there's often patches that you need to put on top of the source code. Ideally, these are for these sorts of reasons, as opposed to trying to make changes that you shouldn't, perhaps, to the upstream code. Once the patches have happened, of course, we then go through the normal build for that particular source code, whatever it is. For the moment, let's assume that it's using this, a standard autoconf way of building things, in which case there's the equivalent of a configure step, so something like a /configure, compile, install kind of build sequence. And again, each one of these is its own task that can be parallelized against other things. From that, we then get an output directory that can be used to build packages, and there's a series of variables that then indicate what files from that that build go where into which package. And indeed, from that, we can then build one of the 3 package formats that are supported. These then go through a series of tests. Now, these are called QA tests, but understand that this is not where you necessarily add your own quality assurance to the tests. These are tests that are used by Bitbake and the build system in order to look for gross errors in what you put together. So once the packages are put together, there are specific things that could be wrong at this stage, and they are pointed out here so that you don't have to find them out the hard way later on. And so the QA steps are essentially looking for packaging errors or formatting errors or binary errors and so on and so forth. So there's a number of very broad tests that happen at this stage prior to the package actually making it into what's called the package feed. The package feed is a part of the output directory. Ultimately is used to provide a place to keep the packages that have been built prior to them being used to actually build images or the SDK and whatnot. Now, in the case of using something like the RPM packaging format, in fact, the package feed is actually kept in a format that can be actually used for doing an upgrade, a DNF or YUM upgrade. In the case of something like the Debian packaging files, in fact, there's an extra step you have to do in order to make a repository from which you can then do the equivalent of an apt-get upgrade. But in any case, the packages that are necessary for that are kept in the packaging feed at this step. From that, there's a second set of, or at least other recipes, I should say, that can be used for doing at least these 2 things. And the first one is image generation. So which packages are then put together in order to make a particular image. And there's extra steps that potentially can come along here, things like WIC and other things in order to build an image that will go on the target. Minimally, the image portion of it will include things like a kernel, perhaps a bootloader of the root file system, maybe a device tree file, and so on. Maximally, if they go through WIC, there will be a binary image that you can put directly onto your storage device on your embedded target. So there's a number of different ways through image generation that will give you the pieces you need to go onto your eventual target. However, separate to that is the building of a development system upon which you can then write code to work with the image that you've just built. From this, of course, we need the various, the compiler and the various development files and libraries and other pieces, include files and so on, that were used to build the image and therefore can be used to modify things on top of that. This gives us the SDK. Strictly speaking, now we use what's called the extendable SDK. This actually provides a fully capable system that allows you to use Bitbake to, in fact, modify what goes into the image itself as you are building new code. And indeed, the ESDK use is now largely used via a tool called DevTool that simplifies the use of the ESDK and actually provides a lot of functionality to work with the image that you've just built. DevTool and ESDK are beyond the scope of this particular talk, but indeed, if you want to go beyond just building an image and to develop code on top of an existing image, those are the things that you'd want to look into further. And indeed, there will be many talks over the next couple of days that refer to and in fact specifically talk about these tools. Okay, so let's talk about Bitbake next. And so the idea here essentially is looking at exactly how these things fit together. Now, the most common form of metadata is referred to as a recipe. This is a BB file. Again, the idea essentially is it provides not only the list of components that make up the thing, the so-called ingredients, but also the cooking instructions, essentially the how do I start from the source code and the metadata that's there to get something at the end that I can then use appropriately. And so what you'll find is there's a series of different recipes that are all built. Some depend on the other, and ultimately by putting them all together, we end up through Bitbake getting packages and then ultimately an image out the other end. So I just got two slides I did. So what do our metadata files look like? Well, there's actually four, technically three, but four different kinds of metadata that you'll find as you go through Yocto Project and Open Embedded. The first one is what's called a BB file. A BB file or Bitbake file is a recipe. This again describes the various pieces that are needed in order to go from source code through to an eventual package, and depending on the recipe, an image. In the case of an image recipe, so that's something we'll be talking about later today. Now, there is a special kind of BB file, and this is something called a package group. In the case of a normal BB file, you are talking about source code and ultimately again, a set of instructions in order on how to build a package. In the case of a package group is a recipe that just depends on other recipes. And so it's an easy way of referring to a group of packages that you want built to eventually go onto your target. It's essentially a meta package, if you will, in order to put things together in a more consistent way. Again, the idea is to try and not repeat yourself as much as possible. If you're always specifying the same group of files that need to go onto a particular image, best to put them into a package group so you can just refer to the package group itself. We also have something called a BB class. This is if you want to think in object-oriented terms, this is a pure virtual class that provides the starting point for other recipes. I always like to describe BB classes as a little bit like when you're baking. If any of you are bakers, if you or for that matter, if you just like eating baking, if you think of different things that are baked, quite often there's the kind of thing, and then there's specifics. So when you go to the store, you buy bread. There's lots of different kinds of bread, but bread is all largely made the same way. The details are slightly different, but the broad strokes are the same. So the idea of a BB class is it's the broad strokes, okay? So your BB class would be it's bread, and then your recipe would say these are the specific things we're going to use for making bread. But ultimately, if you've made bread before, you'll find that the steps are largely the same. The ingredients are similar. Okay, and so that BB class again gives you that starting point for a recipe. And again, it tries to remove as many repeated steps as possible by putting the common things together in that starting point. And you essentially derive a recipe from a BB class through inheritance. We use the inherit keyword in order to inherit from a BB class to make that work. Recipes always end in .bb. BB classes always end in .bb class. These conventions are important. They are assumptions that are made by the tools. Also, where things live in the directory structure again matter. And again, there are conventions on where these things fit together and how they work. And finally, we have configuration files, and these always end in .conf. These also always live in a special directory. You'll find that recipes always live in subdirectories of a recipes directory, recipes dash something, which we'll see a bit later. Classes always end up in a classes directory. Configuration files always end up in a conf directory. You'll find that there are actually several conf directories. There's one at the top level or top dir directory. There's also one per layer. Okay, so .conf files are always in a conf directory or a subdirectory thereof. You'll find that configuration files are largely exactly that. They're variables that are used to configure the rest of the system, either the layer or the entire build itself. And again, we'll go through a number of different configuration files. Now, there are two other metadata files, although these do not work standalone. These are extra pieces that allow you to modify existing recipes to a large degree. One is called a BB append file, and this will essentially allow you to override changes that are made in other recipes. The nice thing about Yocto Project and the open embedded system that's underneath it is that instead of modifying an existing recipe, instead of changing the recipe itself, you can essentially make changes after the fact to it. So again, if any of you are bakers, you will find that what people often will do is they will try a recipe. If it doesn't work quite right, they'll write notes in the recipe book. And you'll find that, you know, depending where you live in the world, flour is a little bit different, or the humidity is different, or whatever. Or maybe the yeast is different. And so you'll say a little bit more of this, a little bit less of that, and so on. BB append files are the same. So you have that starting BB file in a different layer. In another layer, you can write a BB append file that will then make changes to that recipe just for you, because you've included that recipe layer. Without modifying the upstream BB file, you can make those changes that are necessary for the thing that you're doing right now. Again, by overriding the variables that have already been set. And we'll look at the ways of doing that this morning, or at the beginning in this presentation. There's also what are called INC files. Now, INC files are include files. And again, they're also used in such a way as to provide a dry design, don't repeat yourself. It's just that INC files can be included in two different ways. There's the include directive and the require directive. In the case of an include, you are looking for an INC file, and indeed, if you find it, it will be included. However, if it's not found, no big deal. And so you can do optional includes, and indeed, depending on a number of different inputs, it will look for include files in a number of different places. If it does not find it, that's fine. And it means that depending on the version, revision, or name of the recipe you're in fact, you can actually provide different include files without having to use the equivalent of if then else, which is very powerful. So optional includes through INC files with include. Require, on the other hand, is a mandatory require. If it does not find the include file, it will break. And so you'll find that require is used with include files in situations where you have recipes that are highly similar, ones where there's a lot of repeated code. All of the repeated code is put into an INC file, and then each one of those other recipes requires it. What that means is that each one of those recipes has that starting point, which is the include file, and then makes changes to it thereafter. Now, why have BB classes, pardon me, and INC files? They sound very, very similar. Well, the reason why is because in the case of a BB class, you have what's called an ISA relationship. Okay, so it is a derived meaning of that class. In the case of an INC file, there's less structure. Basically, it's just repeated code that you've included. It's more like a header file in C. So just understand that an INC file is largely a localized way of making sure you don't repeat yourself. A BB class, is a more global way of doing that, in such a way that you can make maintenance better and provide commonality across multiple places, certainly across layers with BB classes. So the next thing we have here is the OE core breakdown. I basically run a script that that counts the number of recipes and metadata files in each release for this presentation, just so you can see how it works. So these numbers change every time we give this talk, but certainly for the most recent release, which was Langdale, there are 839 BB files. Now, strictly speaking, there's a few more for package groups and core images, but I pulled those out of the number. For non-package group or core image recipes, there's 839 of them. There's 25 package groups that are a part of this that, again, have dependencies on other recipes. There's 210 BB classes, and again, this typically goes up over time as more and more class files are added. There's 72 configuration files, 300 include files that are used again by a lot of the other recipes, and then finally there's 20 core image files. And again, we'll talk more about images in the second talk today in this room, but essentially, again, these are starting points for building specific images for different targets and so on. Let's see here. All right, just taking my time here. Good. Okay, so the next thing we're going to look at is Bitbake itself. Now, Bitbake itself is a tool that allows you to build things again as quickly as you can. It does its best to ultimately parallelize as many tasks as it possibly can. Now, we're going to look at what a task is in a second. But each recipe breaks down everything into a series of tasks. Those tasks themselves have dependencies between recipes that we don't tend to see, but it tries its best to run as many things as it can in parallel. All those dependencies are built into both the Bitbake tool, and indeed recipe writers themselves, in fact, can provide further dependencies if they so wish. By default, when you run Bitbake, the default task that is run is the build task. And so when you say Bitbake my recipe, it is going to look for a recipe that, again, perhaps oversimplifying, it's going to look for a file called myrecipe.bb, and it's going to run by default the build task or command on it. So Bitbake's basically doing quite a lot when you say Bitbake my recipe behind the scenes. It's trying to automate as many things as it possibly can. Now, if you want to indicate which task you want to run, Bitbake calls these commands, as opposed to the rest of the documentation, we call them tasks. But what this means is when you do a Bitbake -c, you're specifying the task or command that you want run with that particular recipe. So again, in this particular case, there somewhere will be a myrecipe.bb file somewhere in our various layers that have been configured. In this case, we're going to run the clean task on that particular recipe. Okay, and indeed, whatever dependent tasks there are on the thing that we want to run itself. So here we're running clean, here we're running clean all on a particular recipe. Now, the list of tasks, there's a series of tasks that are that you'll find for every recipe, but lots of other recipes have their own list of tasks. You can list which tasks are available for a particular recipe with the list tasks command there. So a Bitbake -c list tasks will in fact list the tasks for a particular recipe. The next thing here is when it comes to building recipes, you'll find that when multiple recipes are provided that have the same name, there may be multiple versions of that recipe. It will always, by default, build the highest version of a recipe. The assumption is that, or at least conventionally, the most recent or highest version is the one that you want. Now, that isn't always the one that you want. And so what you will find throughout Bitbake is there is a series of conventions, and I haven't used that term very much yet this conversation, but there's a series of conventions that are used to define how things work. Following those conventions essentially make it easy for you to remember how it works, and also for others to understand how it works. One of the conventions is that the latest version of a recipe will be used. If you do not want that to be the case, and again, there's situations where you need an earlier version, or maybe a particular version doesn't work with what it is you're trying to build, you can change that in two ways. One is through the default preference, version or the preferred version metadata values. In the case of default preference, you can essentially indicate a number that will essentially be used to figure out the preferred version that you want used. Again, normally it's the highest version number. However, if an earlier version has a higher default preference, it becomes the one that is used instead. So the individual recipes themselves can in fact bump, perhaps you'd call it its importance, and therefore the version that will then get used appropriately. Globally, however, you can also specify what's called the preferred version. And the preferred version will essentially indicate the version that you would like to use if there are more than one option. The reason why it's called the preferred version is because if that preferred version doesn't exist, of course, it will use the latest version that's available. So in the case of preferred version, again, if you've got two options, one of them's preferred, it's the one that's chosen, not necessarily the latest when you use Bitbake My Recipe. You can also specify the version that you want built. And what you'll see here is that we actually call Bitbake My Recipe dash and then the version. What this will do is it will look specifically for version 1.0 of My Recipe to make it work. And then, of course, there's also the idea of working with what's called the revision of the package metadata. This is always an R followed by a number. And so Bitbake My Recipe dash version dash R and then the number appropriately. R0 would be the first revision of the metadata. And indeed, the idea, generally speaking, is that when you change the metadata, you also change the revision of that metadata itself. So whereas the version is the version of the source code you're building with the recipe, the revision is the revision of the recipe that you're using. And so this allows you to uniquely version both your recipe and of course the version of the source code that it's building. Now, normally when you type Bitbake in the name of the recipe with optional version and revision information, it will go and find the recipe somewhere in your layers, your configured layers. However, there are situations where you want to specify the exact BB file you want used. You can do this with bitbake -b and then give the full path to the BB file. You'll notice that you have to end, you're giving the name of a file here, and so it'll actually end in .bb in this instance. You will find this is in situations, generally speaking, when, well, I tend to use this in situations where, for whatever reason, the BB file is not in the search path, not in the configured layer recipe path. Normally because I've made a mistake, and I just want to make sure that it builds. But ultimately, it means that somebody's made a mistake in the metadata somewhere, usually one of the layer files, to make it work. So there's a number of reasons why you might want to do it this way, but this forces the use of a particular recipe appropriately. Yeah, there's a message here, a bit confusing. I was thinking the -c clean is an option in which it cleans first before building it. No, clean just does a clean. There's no build. Unless clean depends on build, clean just does a clean, okay? The thing to understand is that when it comes to tasks, they have dependencies. And so when you run a specific task, its dependent tasks will also be considered. However, if they don't have dependencies, they don't happen. If you run a specific task, the default task, which is build, is not run. So that's the thing to remember. It will only do what you tell it to do. And then, of course, the thing that you're telling it to do will have consequences. The consequence of a clean is not a build. Think about it this way. When you do a make clean, does it then do a build? The answer is no, it doesn't. So think of the tasks as being a little bit like those of a make file. It's not a perfect analogy because, of course, Bitbake is not make. And indeed, do not expect Bitbake to work like make. That's a great way to make incorrect assumptions, but when it comes to the targets themselves, they kind of work the same way. The assumptions that you have with make, though, do not apply to Bitbake for lots of reasons. All right, so the next thing is when you're doing a Bitbake, what you'll find is that when you do a build of something, especially something like an image, of course, there's a ton of dependencies. And so what you'll find is that you end up with a dependency graph starting from the recipe that you've provided. And that will basically start by building a number of different recipes that themselves have their own dependencies and so on. What this means is you have this graph that starts with a few recipes, builds out to a whole bunch of recipes that can be built in parallel, and then back ultimately to the final recipe that you asked to have built, which is quite often an image. What this means essentially is that you have a few recipes where you start with, normally things like your compiler or other sort of core things that are needed, tools and whatnot. And then out to all the recipes that can be built in parallel, and then ultimately down to the last few recipes prior to the image, of course, being built at the end. What that means is if an error happens anywhere within that system, of course, because so many things are being built at once, it is very convenient for most of us to have it break right there and then, so that we can then figure out what went wrong. Now, again, depending on how big your build system is, or build machine, pardon me, is, you can build many things in parallel. Having it break immediately when things go wrong, of course, allows you to then concentrate on what just broke. However, many people don't have, crazy big build machines. What that means is that a build can take a really long time. In some cases, it can take hours. And so what you'll find invariably is that you're going to have a problem. Some people call it a problem, a Murphy problem, one where, of course, the worst possible thing will happen. And a good example of this is, let's say you want to do a build overnight. Let's say you want to kick off a really long build and go home, such that when you come in the morning, it's finished. What can happen, and it certainly has happened to me before, is that you start the build, you go home, and what you realize the next morning is that, let's say you have a 3-hour build on your hardware, and 10 minutes after you left your desk, it broke. Okay, this means you still have effectively a 3-hour build ahead of you, and that's problematic, because it now means that most of your morning is waiting for a build. The reality is, however, is because of the dependency tree, normally where it breaks doesn't actually break the entire build, it just breaks part of the dependency tree. And so instead, what you can do is, when you're first building things, especially if you're not going to be sitting there watching it, running with a -k or a -- continue, it's the same option, one's long, one's short, will allow you to continue past an error. So yes, it will break that particular part of the dependency tree, but it'll do as much of the rest of the build as it possibly can. The reason why this is handy is it means in the morning, when you see that it's broken, what you can do now is build without the -k. It, of course, will show you where the error is. You can fix that. And because most of the build actually completed before, you may only have 15, 20, 30 minutes left of your build. What that means is you haven't wasted all that time that could have been done while you were away. And so when you're building for the first time, and certainly whenever I build a big thing for the very first time, I tend to throw in a -k to make sure that as much as possible is built prior to me coming back and looking at it appropriately. Again, when you're debugging, don't put a -k in there. It just makes things confusing. So the next thing is, of course, and of course, an example here, you'll see we do a -k core image minimal, building core image minimal. Of course, when you're debugging, you would run it without the -k. We will look at debugging recipes later on, however. So again, Bitbake is a task scheduler. It basically will look for a specifically named recipe, and from there it will then, and if I can just ask everybody to keep themselves muted, please. Thank you. So what you're going to find here is that Bitbake ultimately looks for a particular recipe when you run it. Again, it's going to be something that ends in .bb. It's going to be listed in a variable called bb files, and we'll look at the variables in just a second. But ultimately, what it allows you to do is specify recipe by name, that the rest of the system will go and look for that file appropriately in the bb files list, and then run on that appropriately. Each bb file will list a number of different things, things like this, where the source code comes from, the various tasks that will be used, any inherited steps from bb classes, and those kinds of things. And then indeed any changes that you want to make to the default settings or the default mechanisms for building a particular recipe. What you will find is that there are that the metadata and Bitbake will provide sort of a conventional way of building things, but you will find that recipes will allow you to change anything in that mechanism, or to either add to, replace, or do something entirely different than how things are done elsewhere. It is literally anything is possible. Whether or not it's the best way of doing it, within a recipe, you can completely manipulate how things have to be done in order to build your particular thing that you're trying to build. And again, there's better and worse ways of doing that, but what you will find is there's always a way to get from here to there with a recipe, and certainly with Open Embedded and Yocto Project, a recipe that's a part of it. So let's look at some of the default tasks that are there. But in fact, I think the best thing to do at this point, just looking at the time here, is we're roughly halfway through the talk here. I think it'd be a good idea to take a 10-minute break here, just to give everybody a chance to perhaps get some coffee and stretch their legs. So I'm actually just going to quickly start a